neural networks for enhanced unified representation. And so before all of the work, I'm going to introduce what are the graphs. So a graph can be represented as a G equal A and X, which consists of set of nodes. So from this graph, we can see that we have a node set 6 and also a set of edges E, and the edge represents like the link between the nodes. So A represents as the adjacency matrix, and X represents as the node representations. And also we can see graph in almost all applications. For example, in molecular, and the nodes represents the atom, and the edge represents a chemical bond type. And for another example, in social networks, the nodes represent a user, and the edge represent if there is some link between them. And another two examples would be the web networks and also the recommendation. Okay, so I'm going to talk about more about the graph neural networks. Graph neural networks are the most powerful tool in graph representation learning. It involves two layers, one layer for updated layer and the other layer for aggregation. So in update layer, it actually presents projects the graph representation to a new feature space. And then in the aggregation layer, they're gonna, for example, if you wanna update for the node representation 2, they're gonna aggregate its neighbor's information. And in this graph, for update node 2 representation, it will aggregate its one hop neighbors from the node 3, node 1, and node 6. And also, like for the aggregation methods, it could be some min max pooling or the attention. And also the aggregation should be permutation in invariance with respects to the order of the neighbors. When you wanted to study from the L hops neighbors, then you're gonna stack the L gene layers. So for this example is the LGN layers, and it's gonna study for updating the node 1, gonna aggregate information from its 2 hop neighbors by stacking these 2 GNN layers. And GNN can be served to solve the task, for example, the node classification, and use the node representations to predict the node labels. And also can be served to conduct the graph classification by aggregate all nodes representation to predict the graph label. Okay, so from single view GNNs to multi-view GNNs, we want to solve like if we have more than one modality graph representation, how can we learn from these modalities to serve the downstream text better? And for different graph modality, we have few cases. In the real world data, the data source can be different, but they all belongs to describe a same object. For example, in the brain disease prediction, the 2 modalities could be one for the fMRI and the other ones for the DTI. And also we can artificially build more graph structures by conducting the data augmentation. So inherently graph are with more than one structures, so we can compute more graph structures based on the input graphs. And the architecture of multi-view graph neural networks is actually inspired by the 3D shapes recognition in computer visions. Let's see this example. So when you wanted to predict this 3D shape object, there are more than one viewpoint of this shape. So from different view of the shapes, we regard it as one modality. And for each modality, we build like a graph neural network or convolutional neural networks for learning the domain knowledge for these modalities. And then we use a view-wise pooling layers to fuse those modalities representation to one representation. And by assuming this one representation can serve the downstream text for a higher prediction accuracy. So multi-view GNNs looks like this. For the inputs, we have two graphs. Along these two graphs, we probably have a same node size, and also the nodes probably with the same same representation. But among the graphs, the node connectivities could be really not the same thing. And for each modality, we use graph neural networks. And also we use view-wise pooling to fuse the two modalities to one modality. And to solve the problems for the graph classification. And in this fusing process, we have few choices. The first one is the max. We can take the max representation between the two modalities and fuse the max ones to one representation. And also we can take the mean algorithm and also concatenation and the dot production. So what's the problem there? So why we use this architecture? Because graphs are with unique structures. So for each GN can learn the graph structure and learn and can study each modalities. Alternatively, if we use a shared GN parameters, same as the early fused modalities before the graph neural networks, the problem there is the multi-view graph neural networks become meaningless. Because if you want to use the shared graph neural networks, then this only one graph neural networks can only learn one graph structures. So and the cons of this architecture lies in modalities could fall apart for being labeled to different class in a given space. And then another cons will be the different modalities often exhibit distant graph structures, make element-wise fusion due to unclear the node correspondences. And this architecture also cannot learn the inter-modalities relationship. So ideally, the modalities shared inherent some level of correlation so that they share the complementary knowledge and also the shared knowledge. So we want to like this architecture to learn all knowledge from the modalities. To solve those three concepts, we propose adaptive modality-wise structure learning in multi-view GNNs for enhanced unified representation. our work lies in network constructor and the objective function. So basically, we contract two GNs independently, and we add on a layer for modality-wise structural learning before fusing. And then we feed the fusing result. We fuse these outputs to the objective learning for joint learn the graph representation and intermodality relationships. To learn these two tasks, the objective function is designed for two parts. The first part is cross-entropy loss for graph classification task. And then we have an add-on unsupervised learning to learn the distance or the relationships between those two modalities. And specifically, it includes two important components. One is the RAG, which is the adaptive terms that rely on the classifiers performance. And the other term is the optimal transpose distance to compute the interrelationship between the modalities. Okay, now we're gonna give more details about how we're gonna compute the RAG term. First of all, the context of the RAG is strict balance between the distance between modality. So it controls the modality's distance, neither to be too small to cause the overlapped modality and lost the complementary knowledge, nor to be too large to raise the labeling variability and discard the shared knowledge. And to achieve this, the RAG adapt to the classifiers performance. So if we see the prediction value is close to the true label, that means we already have a high accurate classifiers. In this case, we don't need to restrict modality-wise structural learning. Otherwise, when we have a really low performance classifiers, then we want to pose a strict most learning. So in this algorithm, in the line 6, we can see like how the RAG is computed with a more momentary approach. Next, we're gonna give more details about how to compute this optimal transport based between the two modalities. So we probably have a few questions of why we're using the optimal based and how it can solve the concept in multi-view graph neural networks. So the first one, corresponding nodes identification. The question is, due to the unknown graph structure in modality, can we accurately identify their rates, the correspondence nodes? The answer of our optimal based AMoSL answer is yes, and it's achieved this by conduct 4-step computation. The first computation is compute the distance between the modality-wise paired node. And second step is finding the correspondence node. This is by computing the distance and find the small distance between the nodes. Second, the third step lies in identify the importance node in each modality. So this importance can be defined on based on the node degree. And the last step will be construct the structured learning flow between the corresponding nodes based on their importance. In here, we only wanted the important nodes to have their structured learning flow between their corresponding nodes. And our approach can also solve the another questions in multi-VGNs. So this question will be how to ensure that the two modalities do not fall apart in the embedding space and be labeled as the same class. So our approach can achieve this by computing the distance between the corresponding nodes via the optimal transport based. And this is equivalent to minimize the overall structural learning cost and optimize the distance between the modality. And the optimal transport based involves solving linear programming problems to determine the optimal transport flow. This is computed by the F delta ij. And to solve the optimal transport flow is also equivalent to minimize the distance between two modalities, given that the cost factors Cij, which is the determine how far are those two nodes. So as a result, it can solve these problems by construct the structural learning flow between the two nodes and as well as minimize the overall distance between the two modalities. And the results for our work compares to the baselines. So first, AMoSL can give a higher graph classification results compared to all the graph neural networks that use a single view modalities. And then compares to the other multi-VGNs, our work prove its efficiencies to of learning the intermodality relationships in multi-VGNs. Also, we conduct more experiments on why we select the optimal transport distance in our approach. So by doing that, we replace the optimal transport distance to Manhattan distance, Euclidean distance, or cosine distance. But from this result, you can see like the optimal transport distance is the best choice. And we can explain this by for the Manhattan distance, Euclidean distance, or cosine distance, they are targeting at only at to discrete the distance between the modality, but not allow the nodes to communicate with each other. So it cannot define the correspondency nodes across modalities. And the last one is we also determine like how the wrap term effect on the proposed work. So in our work, we define the wrap term is between the 0 and 1. And for zeros means there is no wrap terms, and we don't allow the modality-wise learning between modalities. And when rect equal to 1 means there is always a modality-wise learning. And so rect terms should be tuned between like a 0 and 1. And we can see like when we do not allow the rect learning, the distance will be like really close. And this is not what we want to see, because if the distance between the two modalities is really close, then we might lose the complementary knowledge between modalities. And also when the rect term is come to 0, and means no matter the performance of the classifier, we always wanted to decrease the distance between modality. That's also not a good case, because decrease the two modalities could lose the shared knowledge. So yeah, I think the idea here is basically proof like why we design the rect terms to be adaptive to the graph classifier's performance. Yeah, and that will be all of the work. Thank you. Any questions?
Thank you for your presentation. I would like to know if any questions from forum.
Yeah.